We have covered everything which falls under the coverage of the first exercise set. Now today we'll start with the coverage of the second exercise set, and I sent that by email to you, the second one. That's one. Now you'll start the recitation hours next week. It's on Thursdays. Now, well, then that means you missed 3 recitation hours. Now we can arrange actually for that so that you can make up for that towards the exam. You can have more hours, which I think will be more useful anyway. And I'll be away for some time. I have not talked with Serhat about that, but we can use also, well, we will make up for the missed hours using the spare hour, but you can use the missed hours for recitation as well. But I have to, in order to arrange for that, I have to talk with Serhat. So, and then a conceptual question. Well, there was a question during office hours which can be summarized as, why are we doing what we're doing the way we do it? Is that correct? Okay. So at this point, it might be useful to come to that, because what we'll be doing today is also concerned with that question. Now, the idea can be actually explained by giving an example from real life. Well, you have a knife as a useful tool. Well, it has some functions attached to it, to cut, to pierce. Well, these are the 2 main functions you can do with a knife. And originally, when the tool knife came into being, it was meant to meet these needs. But then we have now a broad spectrum of different knives. They are all referred to by the same name, a knife, but you have knives which are useful for cutting metal, for cutting wood. They're different. Or cutting meat and cutting bread, they're different. It depends upon the texture. Well, you have knives which are sharp on both sides, or which are good for piercing but not for cutting, and so on. So you have a much richer toolbox concerning knives. But there are some basic properties which are shared by all kinds of knives, so that they all fall into the same category. Now, it's similar, but at a different level with mathematical notions. Well, they are also tools, but they are abstract tools which are useful in making an abstract model of relationships pertaining to objective reality. Because we wish to be able to analyze the causality relations. What implies what? Well, in order to do that, we need a theoretical model. You cannot do that just by sticking to the naked reality itself. But in that case, well, take distance, for example. Well, distance, that's a very natural motion which has its origins in reality. Now you see it, there are 2 points on the world which are close, which are far away, how far away, and so on. So that's the rough origin of the notion of distance. But now, Euclidean spaces, they were meant actually to model the space in which we live. But now it seems that that's not exactly the case. Now, first, well, when you live on a globe, if you have a triangle on a globe, that's different than a triangle on a plane. Or if you have the shortest distance between 2 points on a globe, well, if you have a planar map, if you take 2 points, if you just connect them by line, that's not the route an airplane follows in flying from one point to the other, because that's not the closest one. It's the closest on the plane, but it's not the closest on the globe. Or, well, is it just the spherical shape of the world itself, and what about the space? Now, the space has been observed not to be Euclidean space. That's what relativistic mechanics is, relativity theory in physics is all about. So here, you take the notion of a distance, the origin, that originates from real world. And then, in order to have a richer toolbox, you abstract and generalize that. But all the metrics will consider their generalization of the same notion, so they obey the same rules, which we have discovered from the notion of a usual distance. But all metrics which are not similar to the usual distance, which are quite different than the usual distance, they share the same properties, so they are considered to be generalizations of the same notion. But they're useful in different contexts. Now, the problem here is, well, in economic theory, where they will be useful, where a need to define a metric, a generalized distance, which is different than the usual distance, well, sometimes when it's reachable easily, we refer to that, but sometimes that's not reachable at this stage, but they are useful. There are different kinds of metrics which are used in general equilibrium theory. There are different kinds of topologies, which we'll define today, which are very useful in formalizing the continuity, the smooth behavior of set-valued maps and so on. We'll see some of them, but with some, well, that will be left to economic theory itself when you study that, be it macro or micro, makes no difference. So that's the way we do it. We took the inner product, that was the geometric structure, but generalized inner products, they lead to different geometries, and some of them have turned out to be very useful in modeling the physical space, rather than the usual inner product and just R3. Or we took the norm, that was the length of a vector. Now we have different norms, and some of these norms, some of these generalized norms, well, they're being very widely used, well, again, in equilibrium theory, in general equilibrium, in finding equilibria of games and so on. Same with the distance. In fact, more so with the distance than metric. In fact, it will be even more so with the notion of topology that we'll start considering today. So that's the reason why we are doing what we're doing the way we are doing. We start with the rough idea. We find the properties which are decisive in shaping that idea, that notion. Then we generalize that, then we differentiate our toolbox. We widen the spectrum of that tool. Some will be useful. I don't claim it is not the case that each example we consider will be useful somewhere. Well, it might, but life is finite, and you might never come across with something which, where the discrete metric will be the case. That will be the right idea, but this is just to have a wider opinion, a wider horizon in using the tools. Okay, so I wish, because that's conceptually important. So that was okay. Now we have defined metric spaces. The main idea behind topology that was described as finding formal conditions which will tell us when a point is arbitrarily close to a given set. Now, the notion of open and closed sets in metric spaces, that will be an important step forward in that regard. So that's our new section. It is 1 point, I'm not good in counting, what's 6? 6, okay. Open and closed sets in metric spaces. Now we have gone through an imaginary questionnaire with 3 pictures. Which one is open, which one is closed, which one is none. Now we'll come back to that. But in order to formalize the main building block in determining when a set in a metric space is open, let's get back to our very first proposition in this course. It was the following. We took, not very first proposition, but one of the first propositions. We had others as well. We had this. We had Y in R. And we had 2 statements. In one, we started that Y is an upper bound of S. In the other, we started that Y is a lower bound of S. In the first case, we had that Y would be equal to the supremum of S if and only if for every epsilon positive there is some X in S such that Y minus epsilon is less than X. Now, if we draw a picture, if this is Y, and if Y is an upper bound of S, say this is the direction of increasing in real numbers, as usual, then S lies on this side. But for this to be the supremum, this should be the least upper bound. If I take anything less than that, Y minus epsilon, no matter what the positive number epsilon is, how small that is, well, for that not to be an upper bound of S, there should be some X in between, in S. Now, for the lower bound, Y is equal to the infimum of S if and only if for every epsilon positive, now there is some x in S such that y plus epsilon is larger than x. And here the idea is, if y is this, if it's a lower bound, then S lies to the right of that. Well, but for this to be the greatest lower bound, that is the infimum, no matter what point I take to the right of y larger than y, then there should be some x belonging to S less than y plus epsilon, so that y plus epsilon is not a lower bound. Now, here, intuitively using the notion of distance, now we also said the following. Well, this means y is arbitrarily close to the set S. In what sense? Well, no matter how close a point I take to y, there is something in between y minus epsilon and y. I can make epsilon smaller, well, then there is still one point x in here. So, well, I can find arbitrarily close points of the set S to y. Okay? Well, likewise in here. But these expressions are different. Now, the question is, can we find some way of equalizing these? Now, let's check this. If I take this interval from y minus epsilon to y plus epsilon, well, if for each epsilon there is some x in S, then this interval intersected with S, that will be non-empty. Okay? Because there is some point x in S which is larger than y minus epsilon and less than y plus epsilon. But if I do it the other way around, if y minus epsilon, y plus epsilon, intersection S, if that's non-empty, does that imply that there is some x in S with this property? It does. Why? Because y is an upper bound. There is no point of S in this portion. So if y minus epsilon up to y plus epsilon, that has a non-empty intersection with S, those points which belong to the intersection, they must lie in this portion. But then there must be some x in S which is larger than y minus epsilon. Here, we have a similar situation. Let me take this time the interval from y minus epsilon to y plus epsilon. Well, if there is x in S, no matter what epsilon I take, which is located in here, for each epsilon, the interval from y minus epsilon to y plus epsilon has a non-empty intersection with S. Conversely, if that intersection is non-empty for any epsilon, since this is a lower bound, there is no point of S on this portion. Well, the points which belong to the intersection, they must belong to this part. So, for both, I can replace both of these by, for every epsilon positive, y minus epsilon, y plus epsilon, that intersected with S is non-empty. I can write this in both cases, and I'll get exactly something which is equivalent to what I had before. But let me rewrite this in a different way. y minus epsilon, y plus epsilon, I can write this as the set of all x in R such that the distance of x from y is less than epsilon. That's exactly the same. No matter whether x is on the left or right-hand side of y, its distance is less than epsilon from x to y, and that's equivalent, x lying in that interval. But now, since we are in metric spaces, we can, in fact, take, instead of Rd, we can replace R by some non-empty set X, and we can replace D by M. And then take this notion. We will refer to the notion as an epsilon ball about Y with respect to the metric M. Now let's define that. Let Xm be a metric space and Y in X and epsilon positive. Now the epsilon ball about Y with respect to M, this is written as Bm epsilon y. We have y about which the epsilon ball is formed. We refer to this as the radius of the epsilon ball, and this is the metric in question, is defined as B m epsilon y is equal to the set of all x in cap x whose distance from y with respect to this metric is less than epsilon. Now, if we have Rd, an epsilon ball is just this one-dimensional circle, or just an interval about its midpoint. Well, if R2 is taken, the plane is taken with its usual metric, then we have really a circle about the center, but the circle itself not included, the interior of that. If it's R3, then it's a ball, it's a sphere, but that depends upon what x is and what m is. Now for that, let's see an example. Now, since we'll be drawing pictures, let's take again our space as R2, the plane. Now let M1 be the usual metric. That is the usual distance let us take y in all cases 0, 0, the origin of the plane. And well, let's take first epsilon equal to 1. So this is our point y, so it is nothing but this. This is B M1 1 0 0. But when we considered examples of metrics, we had a second example on Rn, on R2 again. Now let me write that. M2 xy, that was defined as xi minus yi, I here from 1 to 2, since we're in R2. That was a metric. We have seen that. Now, let's also draw the one ball about the origin with respect to this metric now. Now, well, let's write what it is. Now, BM2, 1, 0, 0. This is the set of all xy in R2 such that M2 xy minus 0, 0 is less than 1. I'm sorry, M2 xy comma. But when we consider this metric, then this will be 0, 0. So we'll have, well, let me write it like x1, x2. That's better. So to stick to this notation, x1, x2, x1, x2. But this will be equal to x1, x2 in R2 such that now I have x1, the absolute value of that, x1 minus 0, and x2 minus 0, the absolute value of that, less than 1. Now let's draw the picture of this. Now when we're in this quadrant, this means x1, x2, non-negative, but there's some less than 1. Well, if they're equal to 1, then you get this line, but equality is excluded, so you get this portion. But if you go through all the quadrants, you see it's just this. So this is now the one ball about 0, 0 with respect to M2. So that's different. Now, finally, as the third example, let's consider this weird discrete metric. That is, M3 of xy is 1 if x is different than y, and it will be 0 if x is equal to y. Now, M3 xy, that will be 1 if x is different than y, and 0 if x is equal to y. Now, if we consider B M3 1 about 0, 0, what will that be? This will be the set of all x in R2 such that M3 of x 0, 0 is less than 1. But what's this set? If x is different than the origin, 0, 0, m of x 0, 0, that will be 1. 1 is not less than 1. So the only point in R2 which satisfies this inequality is when x is 0, 0, the origin. So this is equal to, so that's this point. BM31 0, 0. Now let's go through the same exercise when epsilon is equal to 2. Well, it is clear that this will, this time, be larger, but will have the same shape. It will have radius 2. Likewise, for this, it will become just this shape. 1 will be replaced by 2. This will be the set of all points x1, x2, such that x1 plus x2 is equal to 2 in the non-negative quadrant. That will be this. You will have this. But what about the discrete metric? What will be M3? 2, 0, 0 be. It will be everything, the whole plane. Because no matter what point in the plane you take, its metric distance according to the discrete metric is 1, and 1 is less than 2. Everything is too close to, as the number 2, too close to this. So these neighborhoods may behave quite differently depending upon the metric. Now, we are always, well, the naming, and when we try to draw the picture of a situation, we use the plane and balls, that is, we draw the pictures as if they were according to the usual distance. We'll continue doing that, but there is a rule concerning pictures in mathematics. Try to draw the picture of a mathematical situation. That's useful all the time. But don't overtrust it. It might be misleading as well. Drawing pictures is useful, but sometimes pictures are misleading. Okay. Now, we can define what we mean by an open set with respect to M finally. We'll use the yardstick which we discovered at the end of last time. Now let Xm be a metric space. And a subset of X. We say that A is open with respect to M if the idea was for each point in the set cap A, there should exist a small enough radius epsilon, a positive real number epsilon, such that the epsilon ball about that stayed entirely within the set. We'll take that, but now with the generalized epsilon balls. If for every X in A, there is some epsilon positive. This will depend upon X, of course, such that the epsilon ball with respect to M about X stays entirely in A. We say that A is closed with respect to M if its complement the complement of the set cap A with respect to X, that is the set difference, X minus A, that is the set of all points in cap X which are not in A, is open. With respect to M. Okay? Now let's go through some examples. But the first two examples will be general examples, so let me just write that in the form of a proposition. Now, let Xm be a metric space. Now let us first consider the two extremes, the empty set and the entire space. What can you tell about the empty set? Is it open according to this definition? For every X in the empty set, no matter what statement follows that, that will become a true statement because there are no members. Well, for every X in the empty set, X is a pink elephant. That will be a very true statement. But for every X in the empty set, well, there is some such thing. Okay, so the empty set is open. What about the entire space? Well, if you take any point in the big space cap X and any epsilon, the very definition of an epsilon ball that consists of members from cap X, so that will be a subset of cap X. So these are both open. Now what about closedness? If they are both open, the complement of the empty set is the entire set cap X, that's open. The complement of this is the empty set, so they are both closed as well. Both open and closed. So closed and open are not negations of each other. That's crucial. You can have sets which are both open and closed. You can also have sets which are neither open nor closed. Secondly, we have defined openness in terms of an epsilon ball, in terms of epsilon balls, but we can now consider epsilon balls themselves as sets in the given metric space and ask whether they will be open or closed or not. For every y in X and epsilon positive, the epsilon ball about y with respect to m, that will be open. Let's quickly go well, we have gone through 1, 2. Now take any y in X and epsilon positive. Now, let's draw a picture. Well, no matter what M is and what cap X is, let me draw the epsilon ball like this with radius epsilon. Now, in order to conclude that this set, B epsilon my, is open, we need to consider any X in this set and check whether there is some positive epsilon prime. such that when I take the epsilon prime ball about x with respect to m, that entirely stays within this set. Okay, but now this distance is mxy. What's this distance? That's epsilon, the radius of this. Now, if I take the radius of the ball about x, this, which will be the difference between epsilon and mxy, pictorially, that seems to be doing the job. So let's try that. Pick any x prime in the epsilon ball about y with respect to m. Now, the epsilon, well, since we have used epsilon here, let's use epsilon prime here. Now we wish to find some epsilon prime such that the epsilon prime ball about x prime is entirely contained in this set. Well, let's take it. Well, let's first note then, by definition of the epsilon ball, mx prime y, that will be less than epsilon. That means epsilon minus m of x prime y, that will be positive, and let me take that as epsilon prime. Now let's check whether this epsilon prime does the job. What does that mean? Well, that means we will check whether the epsilon prime ball about x, not, okay. So I'll take it like this. Now let me take just here these x's. I have not used x. It's misleading to take, I mean, no problem, but let's just, in order to this is, I take this x, okay, we have this. Now, what we wish to show is that the epsilon prime ball about x, that entirely stays within this. So take any x prime in the epsilon prime ball about x with respect to m. We take anything in here, and we wish to show that is a member of the big ball. But for that, I need to, well, let me first write. Then, by definition, this is m of x prime x, that's less than epsilon prime. Okay? But let me write what epsilon prime was. This was epsilon minus m of xy. So, let me continue here. This means m of x prime x plus m of xy is less than epsilon. M of x prime x plus m of xy, that's less than epsilon. I just carried this over to this side. But what do we know about this? M is a metric. So far we have not used any properties of the metric except for that they're non-negative. But this is by triangle inequality less than or equal mx prime y is less than or equal to this. But that simply means x prime is in epsilon ball about y with respect to x. Now we have picked an arbitrary member in this set and have shown that that belongs to this set. Thus, the set we started with, Bm epsilon prime x, that is contained in Bm epsilon y. But x was an arbitrary member in here, so for each point in this ball, there is a ball about the point we take, which entirely stays within the ball that we started with. Thus, so Bm epsilon y is open with respect to n, completing the proof. Can you say anything about whether this ball is closed or not? Not yet, and it will turn out that it's closed in some cases and not so in other cases. But now, using this proposition, we can get the following result. Now let me refer to these as examples. Now let A be less than B, or A be in R with A less than B. Let's consider this interval. This interval in R, now that's defined entirely in terms of the order structure of R. It's just the set of all x in R, x, A less than x, less than B. This is the definition of this set. But we refer to this as an open interval. Now let's check whether it's open with respect to the usual metric on R. Can we do that easily? Well, we can actually, this is A, this is B, this is the interval. Is this an epsilon ball about a point for some epsilon? Yes, take the midpoint, which is A plus B over 2, and this radius, that's B minus A over 2. Now set y equal to A plus B over 2 and epsilon equal to B minus A over 2. Okay, now, so AB, that will be the epsilon ball, with epsilon being this. With respect, I will show the usual metric, since it's the distance by d, about y. So this is open, because we have shown any epsilon ball about any point is open in a metric space. Now, well, we could have, of course, gone what we have done in this general setting, we could have done in this particular setting as well. But since we have this, now, will AB, which is just the set of all x in R, such that A is less than or equal to x, that less than or equal to B, is that open? No, because I will not write that in full anymore, but A is in here. If I take an epsilon ball with respect to the usual metric, well, that cannot be contained because it will have points which are less than A. So it's not open. Is it closed? Now for that, you will take its complement, R minus AB. That will be the interval from minus infinity to A and the interval from B to plus infinity. But you can check easily that this is open because if you take any point in here, it will be less than A. Just take A minus that point as its radius. If you take anything in here, it will be larger than B. Just take the radius, that point minus B. They will be epsilon balls in here. Now, check that. This is open, so AB is closed. Now, let us go to our weird metric, the discrete metric. Now, let X be any non-empty set and M the discrete metric on X. That is, mxy is 1 if X is different than Y, 0 if they're equal. Take any A Can we say anything about whether the set is open or closed? In R2, for example, if you take any set, well, it may be closed, it may be open, it may be none. But here, let us try to show that this is open. Now assume that X is in A. Can we find an epsilon ball about X which entirely stays within cap A? Well, if that's the case, then the only thing about cap A we know is that X is in there. That information should suffice. But set epsilon, say equal to 1, in fact. Now, the epsilon ball about M, which is the epsilon ball about X with respect to M. What's this? This is the set of all members of cap X, say Y, such that mxy is less than 1. But just X satisfies that, and no Y different than X, because mxy is 1, and 1 is not less than 1 if Y is different than X. So this is just singleton X. As was in the example, it was singleton, the origin only, but X is in A, this is in A. So, A is open. This means every set under this discrete metric is open. What about closedness? Well, if every set is open, every set is closed as well, because given any set, you take the complement. The complement is a subset that's open. So every set is open. So every subset of X is open. Hence, every subset of X is closed as well. Now we'll see further examples of open and closed sets anyway, but let's follow the abstraction process that we have been following so far to take one more step. Now here, we generalized the notion of distance, obtained the notion of a metric, and we used metric in terms of epsilon balls to determine whether a given set was open or closed. Okay? Well, one way could be, well, we can start with a non-empty set. We can consider its power set, that is the set of all its subsets. We can single out as the point of departure. We can actually label some of those sets being open and some being closed. But if we do that in an arbitrary manner, that does not make much sense. You cannot go one step further than that. But if we actually now specify what decisive properties open sets in a metric space satisfy, and take the list of those properties as the defining condition of specifying a subcollection as the subcollection of open sets, well, that might work. So the next step is to find what properties open sets and closed sets satisfy in a metric space. Well, what should that mean? Well, openness and closeness, that's something which pertains to sets. Well, a natural question now is whether that attribute, that property, is being preserved under set operations. What kind of set operations do we know? Well, we have the best known and the widely used ones are union, intersection, and taking the complement. Now, we have some idea about the complement. The complement of an open set is closed, or the complement of a closed set is open, that we know. But let's check what happens under union and intersection. Now, let Xm be a metric space now, as the first condition, let us note down something we have already observed. No matter what the metric is, the empty set and the entire space are both open and closed. The empty set and X are both open. Let me write those pertaining to closed sets in red. Well, they are both closed as well. Now let's consider the union, it will turn out that the union over any non-empty collection of open sets, well, whether that collection is finite, infinite, countable, uncountably infinite, irrespective of that, the union will turn out to be open. So, the union of any non-empty collection of open sets is open. But as for closeness, closeness will be preserved under intersection of any non-empty collection of closed sets. The intersection of any non-empty collection of closed sets is closed. The next natural question is, of course, what happens to open sets under intersection and what happens to closed sets under union? The preservation there will be confined to finite non-empty collections of open and closed sets respectively. So thirdly, the intersection of any non-empty finite collection of open sets is open. This time, the union of any non-empty finite collection of closed sets is closed. Now let's go through the proof of this, which is simple but telling. Now we have done statement one anyway, so proof one already done. Now two. Well, then let's consider the first open version. Now let I be any non-empty set, just an abstract set, and assume that we have a collection which is labeled by the members of the set. We can represent each collection via an index set, such that each member in that collection is open. So G alpha is open for each alpha in I. So here, of course, we have just a metric, openness with respect to that metric. Since that's clear, we do not mention that. Now, we wish to show that the union of these G alphas, that's open as well. Assume that X is a member of that union. But then, we should be able to produce an epsilon ball about X, which entirely stays within this set in order to conclude that this set is open. But by definition of union, X belongs to at least one of these G alphas. X belongs, say, to G beta for some beta in I. But what do we know about G beta? It's open. So there is some epsilon such that the epsilon ball about X, that's entirely contained in G beta. Since G beta is open, there is some positive epsilon such that B M epsilon X is contained in G beta. But how is this G beta related to this union? Well, it's contained in that union. But now we have produced some epsilon ball about X, which is entirely contained in this set, just implying that this set is open. So, union G alpha, alpha in I, is open. Now, let's go through the same exercise for the closed version. Well, again, this time, let J be any non-empty set, and say A gamma is closed for each gamma in J. Now we wish to show that the intersection of A gammas, that's closed as well. But the definition of closeness, that's in terms of the openness of the complement. So let's consider the complement of the set, which is equal to the intersection of these A gammas. X minus the intersection of A gammas, gamma in J. But what does this remind you of? There's some famous law concerning equality of sets. De Morgan's laws, by De Morgan's laws, this is nothing but union of the individual sets. In fact, it's trivial to show that this set equality holds. Let's go through that in words. Well, if some member belongs to here, then it's in cap X, but it's not in here. It's not in here means that member does not belong to A gamma for at least one gamma. It does not belong to all of them. It belongs to the intersection if and only if it belongs to all of them. But there is some gamma which does not contain, but then X minus of that A gamma, that contains the point X. So, well, at least one of these containing that point means the union contains that. The converse is similar. But now we're finished. But x minus a gamma is open since a gamma is closed for each gamma in J. But by what we have shown above, this union of open sets is open itself. By what we have shown above, but that's just this complement. So intersection H gamma, gamma in J is closed. Now, well, 3 follows a similar line, so that's left as an exercise to you. In mathematics, if you have some such restricted statement, it is always the case that, well, you check whether this restriction to finite collections is justified or not. Well, this may be a true statement, but a much stronger statement might be true as well. Now here, we'll see 2 examples showing that in 3, this finiteness condition cannot be discarded. It has to be kept. That is, we will give an example of an infinite collection of open sets whose intersection is not open, and an infinite collection of closed sets whose union is not closed. Now let's consider R together with this usual metric. In R, we know that open intervals are open in the sense introduced here as well. So, for each natural number, now let's consider as Gn the interval from 1 minus n to 1 minus 1 over n to 1 over n. This is open. Gn is open for each n in n. Now let us consider its intersection. What will this intersection be? Now the intersection will contain 0. 0 is Gn for all n, but can it contain anything else? Take anything positive. Well, if n gets large, there is some n prime such that minus 1 over n prime, 1 over n prime will not contain that point. If it's negative, similarly, so this is equal to singleton 0. I will not write the details, but I guess it's clear. Is this open? No, it's not open with respect to D. No matter what epsilon you take, an epsilon ball about 0 is the interval from minus epsilon to plus epsilon. It contains, for example, epsilon over 2, which is different than 0. This is not open. Two, again, for each n in n, let us set a sub n equal to 1 over n, 2 minus 1 over n. When n is 1, this is just singleton 1. But then, well, for 1/2, 3/2, and so on. But these are all closed intervals, although we have left that as an exercise to you. We noted that a closed interval in R is also closed in the metric sense when we use the usual distance. So an is closed for each n. Now, consider the union of these ANs. What will it be? Well, 1 over n, that will become arbitrarily small as n gets large. So we can by taking n large enough, we can make everything which is less than 1 but positive to be in here. But 0 will never be there. In fact, here as well, you can check, so let me write it, check that. This is just this interval 0, 2. This is open, but what we need to note here is not that this is open, that this is not closed. Because in general, we know not open does not mean not closed. But here, each of these was closed, but this infinite union, this is not closed because its complement is not open, which can be checked easily, is not closed. So we have given one example for each statement in 3. If we leave out the finiteness condition, then the conclusion need not hold. But what we'll do now is we will take open sets as our primary concept, as our point of departure, and as for consistency conditions, we will take these 3 conditions as the defining properties of a topology. We could have done that with closed sets. That's perfectly doable. And we'll see that can be done in many different ways, but for that, we need to define and examine topological spaces to some extent. So that takes us to our next chapter, which is on topological spaces. Any questions about what we have done so far?